Welcome back to our DC circuit series. Today, we're taking our first real look at circuits that change over time. Up until now, everything we've worked with has been steady state. But have you ever wondered what actually happens during the transition? Right when you flip a switch or connect a source? Well, the answer is really interesting and surprisingly intuitive. For now, we're going to focus on circuits with only one energy storage element, which are modeled using first-order equations, thus first-order circuits. A first-order circuit is simply that, a circuit with one energy storage element, either a capacitor or an inductor, along with resistors and voltage or current sources. By the end of this video, you'll understand how capacitors and inductors respond over time, what the time constant means, and how natural and step responses behave. Before we dive any deeper, I want to take a moment to thank our friend of Circuit Bread, Digilant, for supporting this lesson and so many other DC circuits lessons. Support us by going to their site and seeing if they have any tools that can help you in your electrical engineering journey. So, as a reminder, capacitors store energy in an electric field and resist sudden changes in voltage, while inductors store energy in a magnetic field and resist sudden changes in current. Having a single storage element in a circuit is enough to make voltage and current change gradually rather than instantly, following smooth exponential curves. And we can use those curves for our benefit. So let's start with the natural response. Imagine you charge a capacitor and then disconnect the battery. The capacitor doesn't drop to 0 volts immediately. It slowly releases its stored energy through the resistance in the circuit. The speed of that decay is set by the time constant tau, which looks kind of like a weird lowercase t. But tau is very important. For an RC circuit with a resistor and capacitor, tau equals R times C. For an RL circuit with a resistor and inductor, tau equals L divided by R. The bigger the time constant, the slower the circuit changes. So in this natural response, where the circuit responds naturally after any outside sources are removed, how quickly the voltage or current dissipates is reliant on how much energy is stored in the capacitor and inductor, as well as how much energy the resistor dissipates at any given moment. Let's connect this behavior to some simple math, just enough to understand the shapes of the curves. Mathematically, the natural response of a capacitor's voltage looks like this. V of t equals V0 times e to the negative t over tau. At time 0, immediately after the external source is removed, the voltage is V0. As time increases, the exponential term shrinks towards 0, and the voltage fades away smoothly. Now, you don't need to memorize these equations, just recognize their shapes and what they mean, and you'll be good. And let's go the other direction and look at the step response, which is what happens when we apply a sudden change, like connecting a discharge capacitor to a voltage source. If you're not familiar with a step function, it is simply a function that has an output that goes from 0 to 1 at time equals 0. It looks like a step, thus, step function. I love the naming. Anyway, at the moment the source is connected, the capacitor's voltage is 0, and as soon as the outside source is connected, the current is high as the capacitor is quickly charging. But as it charges, the voltage rises, the current falls, and the capacitor gradually approaches the supply voltage. Now, this is represented mathematically by V of t equals V sub s times 1 minus e to the negative t over tau. See, there's that tau again. In this case, at time 0, the exponential term is 1, so the voltage starts at 0. As time goes on, the term shrinks and the voltage approaches V sub s. After one time constant, the circuit reaches about 63% of its final value. After about 5 time constants, it's essentially at steady state, and you can start thinking of it as a normal DC circuit. I've been focusing on RC circuits because they're slightly more common than RL circuits, but RL circuits with the resistor-inductor relationship behave the same way. However, instead of voltage change exponentially, we typically watch the current change exponentially. Swap out voltage for current, and the math and concepts are basically interchangeable. So let's talk about why this matters in real circuits. The reality is that first-order behavior shows up in a huge range of real circuits. RC circuits appear in filters, timers, sample and hold circuits, and power supply smoothing. RL circuits appear in motor control, relays, power electronics, and signal shaping. And while RC and RL circuits are a simplification, there are many times that complex circuits often behave like first-order circuits when you look at how they respond over time. Understanding tau and time constants, as well as exponential behavior, gives you the tools to analyze everything from sensor conditioning to switching regulators. As we go through these DC circuit concepts, it's very easy to get behind, start getting things jumbled in your head, and get lost in the details. When you're doing these problems, the math is no joke, but I encourage you to take your time and make sure you're working to understand the basic concepts and tying them to these simple math equations I shared. So the key things to remember are that first-order circuits have one energy-storing element, its behavior over time follows exponential curves, dissipating when looking at the natural response, growing when looking at the step response, and the time constant tau tells you how fast those changes happen. All right, in our next lesson, we'll explore second-order circuits, where we introduce a second energy storage element and begin to see oscillations and resonance, so things are going to get even more exciting. I want to thank Digilent again for their continued support of this series. If you found this video helpful or interesting, give it a like, subscribe, and we'll catch you in the next one. Take care.
Hey, we hope you enjoyed this video. Did you know that circuitbread.com does more than just tutorials? Besides tools, textbooks, and other things, we host an ever-growing library of math and electronics-related equations and glossary terms. Don't have the entire table of integrals or Faraday's second law memorized? We gotcha. Go check them all out.